A long time ago in a galaxy far, far away, two powerful forces were grappling fiercely, locked in a titanic struggle. No, it was not the Empire and the Rebel Alliance, different galaxy. It was a pair of black holes, each about 30 times as massive as our sun, locked in a spiral orbit. As they circled each other, they slowly leaked energy away in ripples of gravitational radiation, causing them to spiral closer and closer together and to orbit faster and faster like a figure skater pulling in her arms. Finally, in a last fraction of a second, they spun together in a massive collision, sending out a burst of energy greater than the output of 1 billion trillion suns. Fast forward to the present, 1.3 billion years later. On September 14th, 2015, a wave front of that energy burst finally reached the Earth. It swept through two observatories, one in Washington State and the other in Louisiana, shaking them by an infinitesimal amount. And for the first time in human history, this kind of infinitesimal shaking was captured and measured by the most sensitive device ever built by human beings. A device so sensitive, it can measure a change in its own size that's 1 billion times smaller than the size of an atom. This was the first ever detection of a gravitational wave, a wave of gravitational energy first predicted by Albert Einstein a century ago. Einstein assumed it would never be possible to detect these waves because they're just too small. But now, after decades of effort by thousands of scientists from all over the world, they've finally been detected. This is easily the most important astrophysical discovery of the new millennium. It was deservedly greeted with celebration and front-page headlines. Three of the people who pioneered this effort were just awarded the Nobel Prize in Physics in 2017. Now, for me, this discovery had a personal significance. I have a PhD in relativistic astrophysics. This is me at the blackboard. And my work was somewhat related to this experimental effort. Now, I was never involved with the experimental teams who actually build these detectors. They don't usually let me near working machinery. But I did work alongside colleagues who were part of this effort, and I followed their progress with great interest. So when I saw that these years of effort had finally paid off in a major scientific breakthrough, I was thrilled for my former colleagues. But the news also reminded me of some of the challenging philosophical questions that this whole area of physics raises. Gravitational waves are often described as ripples in the fabric of space-time. What does that even mean? What is space-time? Is that even a valid concept? Black holes are sometimes described as objects that have infinite density. But we know that there can't be an actual infinity, so there must be something wrong with that idea. Are black holes even real? Or is all of this just sort of rationalism on steroids? Now, I think it can be tempting for people to be dismissive of this whole area of physics, especially some objectivists. Objectivism has a very clear absolutist perspective on metaphysics. It can be tempting to assume that the objectivist metaphysics leaves no wiggle room for space-time wiggling. And when we see a news report claiming that scientists have detected ripples of curved space-time, it can be very tempting to assume that this is just automatically ruled out on metaphysical grounds and to dismiss the whole thing as nonsense. In my view, this would be a grave mistake, though. It's important to recognize that metaphysics is a very delimited science. And it's important to distinguish between claims that actually contradict reality versus claims that, while they might strike us as strange and hard to understand, don't necessarily contradict the basic nature of reality. Now, I'm not a philosopher or a philosopher of science, and I don't claim that I can give you definitive answers to all of those philosophical questions that I raised. And that's not the purpose of my talk today. What I do plan to do is to try to give you an idea of what these gravitational waves are, how we discovered them, and why it's so valuable that we can now detect them. So to do that, we'll have to go on a tour of some interesting areas of physics, and we'll have to spend some time talking about Einstein's theory of gravity and the evidence that supports it. Now, for what it's worth, I will say this. I do not think that there is necessarily an inherent conflict between general relativity and the metaphysical principles that we know to be true based on objectivism. I think there are challenging questions that need to be answered in order to integrate them properly, but I don't think there's an inherent obstacle to doing so. I view this as an open area of research, and a particularly interesting one. Now, before we plunge in, let me give one word of reassurance. I know that some people are terrified at the very idea of a lecture on physics. So I wanted to make sure that this material would be clear and interesting to a general audience. So the standard I used was that if I could explain things in a way that would be clear, if I could explain things in a way that my 13-year-old daughter would understand, then it could stay in the talk. And I'm happy to report that everything I'm going to talk about today has passed the daughter test. Now, on the other hand, some of you have met my daughter, and yeah, you may have noticed that she's really smart, so you'll still have to pay attention. So what are gravitational waves? Where does this idea come from? Well, gravitational waves are a prediction of Einstein's theory of gravity, the general theory of relativity. In 1905, there he is, Einstein published his special theory of relativity, which radically changed our understanding of space and time and motion, especially motion at speeds close to the speed of light. By the time he published his special theory of relativity, he also had a number of lines of evidence suggesting the need for a new theory of gravity. And he developed a theory that extends Newton's law of gravity to account for these new lines of evidence. Now, if you took science in high school, you probably learned that Isaac Newton viewed gravity as a force of attraction between massive bodies. The idea is that every massive body in the universe attracts every other massive body in the universe. And Newton's law of gravity tells you how strong that force of attraction will be. The bigger the masses, the stronger the force, and the farther apart they are, the weaker the force. Now, one question that Newton's theory does not answer is the question of how the gravitational force gets from one mass to another. If I have one mass over here and another mass over here, how is it that these masses pull on each other? Do they just act on each other somehow across the distance between them? Or is there some kind of signal that travels between them and carries the gravitational force? What if they're billions of miles apart, like Pluto and the sun? How does the sun pull on Pluto across billions of miles? Now, Newton recognized that some kind of answer to this question is needed, but properly, he did not want to venture any guesses that went beyond the evidence that he had available. He knew that his law of gravity was correct based on the evidence and the data that he had available, and he didn't really have evidence that would shed light on this question. So the solution to this question of action at a distance came centuries after Newton. And it came from work that scientists were doing in a totally different area of physics. It came from the study of electricity and magnetism. Now, it will help us a lot in understanding Einstein's theory of gravity and the nature of gravitational waves if we spend some time on those developments. I'm going to spend a little bit of time talking about electricity and magnetism, and then we'll come back to Einstein and gravity, okay? Now, I assume that most of you are familiar with magnets. You probably played around with them as kids. So you know that magnets also exert forces on each other across a distance. If you take the north pole of one magnet and you bring it near the south pole of another magnet, they will attract each other. You can actually feel the attractive force between them. right? So this is very similar to the force of gravity. It's an attractive force that acts across a distance. Now, magnets are a little complicated because they have north and south poles. Two poles of the opposite type attract, but two poles of the same type will repel each other. But in either case, whether they're pushing or pulling, the force acts across a distance. So they're a little more complicated than gravity, but there's nevertheless a basic similarity. It's this idea of action at a distance. The same thing is true of electrical forces. Objects that are electrically charged can exert forces on each other across a distance. And there are two kinds of electric charge, positive and negative. So it's similar to the case of magnetism. Opposite charges attract. Objects with the same type of charge will repel each other. So there's all kinds of examples of this. So how do all these forces act across a distance? Well, the answer to this question came in the form of a new concept that scientists developed in studying electricity and magnetism. And that's the concept of a field. So let's talk about the concept of a field. What is a field? Well, imagine you have a magnet. The magnet gives rise to something in the space around it called a magnetic field. The magnetic field is some kind of magnetic property that exists all around the magnet but is distinct from the magnet. So it's a basic kind of magnetic stuff that's associated with magnets. Now imagine that your magnet is exerting a force on a piece of iron. How does this work? Well, the idea is that the magnet does not somehow just exert a force directly, instantaneously across space. It has this magnetic field that spreads out all around it. And the magnetic field extends out to where the piece of iron is. So what the iron encounters is the magnetic field at its own location. The magnet doesn't act on the iron directly across space. It acts through an intermediary. It acts through this magnetic field. Now, some of you may have played around with iron filings scattered near a magnet. Has anyone ever done that before? So if you do that, what you'll see is this characteristic pattern. Seen this before? So the magnet is surrounded by its magnetic field, and each little iron filing there is being affected by the magnetic field that exists at its own location. So it's sort of like dusting for fingerprints. This shows you what the magnetic field looks like in the vicinity of the magnet. So the concept of a field helps to explain how these forces operate. If you have a magnet, it's surrounded by a magnetic field. Anytime you have a magnet, and the field spreads out across space, and this is how it interacts with pieces of iron or with other magnets. The same idea applies to electrical forces. If you have an electrically charged object, the idea is that the charge gives rise to an electric field in the space around it. And the electric field is what interacts with other electric charges. Now, of course, we can also apply this idea to the gravitational force. The idea is that a massive body like the sun has a gravitational field that extends out into space. So the sun doesn't pull directly on Pluto across a space of billions of miles. Rather, what Pluto is experiencing billions of miles away from the sun is the sun's gravitational field. Now, of course, we can't forget about the most important force. As it turns out, the concept of a field is a key part of the explanation of the force. So the concept of a field is very useful in explaining how forces operate. But it raises a new question, and that is, how do fields operate? So we can accept the idea that these fields exist and that they're somehow related to the magnets or the charges or the masses that give rise to them. But how do these fields behave? What are their properties and characteristics? Are there laws of physics that we can define that govern their behavior? Now, in the case of electric and magnetic fields, the answers to those questions came from the work of a Scottish scientist named James Clerk Maxwell. Maxwell is one of the greatest physicists of all time. I'd say the top three are probably Newton, Einstein, and Maxwell. And what Maxwell did was he defined the laws that govern all of the behavior of electric and magnetic fields. In the 18th and 19th centuries, there was a lot of work done by many scientists on electricity and magnetism. Some of it was experimental, some of it was theoretical, but the crowning achievement of all of this was Maxwell's work. Maxwell took all the previous work that had been done in this area, and he boiled it all down to a set of mathematical equations that govern all electromagnetic phenomena. This was such an important feat of integration that these are now known as Maxwell's equations. Now, I wasn't going to show you Maxwell's equations. Supposedly, there's a law of physics talks that says that for every equation you show, you'll lose half your audience. And there are 4 Maxwell equations, so this would be a disaster. But I will say this. Maxwell's equations are such an awe-inspiring feat of integration that you sometimes see physics students walking around campus with them on a t-shirt. So this is what passes for cool in the physics department. Okay, so Maxwell's equations codify everything that's known about electric and magnetic fields. And they express the physical laws governing the behavior of the fields. Now, the power of all this is once you've got everything boiled down to a small set of equations, you can work with those equations to see what you can learn from them. Just by applying the rules of mathematics to the equations, you can gain new insights into the behavior of the fields. And this is exactly what Maxwell did. Just by playing around with his equations, by purely mathematical means, Maxwell discovered new things about electricity and magnetism that were absolutely revolutionary. I'm going to tell you about 3 of them. One thing that Maxwell discovered is that electric and magnetic fields can propagate as waves. In other words, you can generate waves of these electric and magnetic fields that travel from one place to another. What does this mean? Well, think about the kind of waves you're familiar with. Ripples on a pond, or waves that you can make by shaking a rope or a slinky. So you have a disturbance over here, and it causes periodic vibrations that propagate out as a wave. Well, physicists know how to describe waves mathematically. So if you have a physical situation like the pond or the slinky, a physicist could tell you how to write down a set of equations that would describe those waves. Now, whether you'd want her to do that is a separate question, but the point is she could show you the equations that describe the waves. Now, what Maxwell did, just by playing around with his equations, he found that he could put them in the exact form of the equations that govern waves. And the implication of this is that electromagnetic fields, which obey his equations, ought to be able to travel as waves. Now, it's important to note, nobody had ever observed electromagnetic fields behaving like waves. So this is a purely theoretical prediction just based on the equations, based on Maxwell's field equations. But it raised the question of whether these waves actually exist in nature. According to the equations, they could propagate as waves, but do they? I mean, do these electromagnetic waves actually exist? Well, the second thing that Maxwell discovered is that these electromagnetic waves have all the properties and characteristics of light waves. So people have been studying the properties of light for centuries. And by Maxwell's day, there was a ton of things that people knew about how light behaves. They knew that light can be reflected by a mirror. They knew that it can be refracted or bent by glass or other materials. There were experiments that people had done to try to measure the speed of light. So they actually had pretty good estimates of how fast light moves by this time. And there were a whole bunch of other things that people knew about light. Now, what Maxwell found, again, purely by playing around mathematically with his equations, is that these theoretical electromagnetic waves of his have all the exact same properties that light has. These waves can be reflected, they can be refracted. The equations even tell you how fast these electromagnetic waves have to move. And the wave speed turned out to be exactly the speed of light. So the implication of this is pretty clear. Maybe light just is a type of electromagnetic wave. Maxwell proposed this idea, and it turned out to be true. Today we know that light is just a type of electromagnetic wave. So these esoteric, theoretical waves that just sort of popped out of his equations turned out not only to be real, but to be related to something completely commonplace and familiar, namely light. So this was an incredibly powerful feat of mathematical ingenuity. The third thing I want to tell you about what Maxwell discovered is that these wave equations of his are very general. One important property of a wave is its wavelength, the distance between two peaks of the wave. And there's nothing in Maxwell's equations that sets any kind of limit or restriction on the range of wavelengths that are possible. Now we know that light waves have a fairly narrow range of wavelengths. They go from the violet end of the rainbow with a wavelength of around 400 billionths of a meter to the red end of the rainbow at around 700 billionths of a meter. So there's not a lot of variation there, right? But there's no reason why you couldn't have electromagnetic waves with completely different wavelengths. So Maxwell's equations actually predict that there should be a whole spectrum of electromagnetic waves with a much wider range of wavelengths. Now again, this is a purely theoretical prediction. Nobody had ever seen waves other than light waves before, right? But a couple of decades after Maxwell published his work, a German scientist named Heinrich Hertz went into his lab and tried to see if he could actually generate and detect Maxwell's waves using electromagnetic equipment. And lo and behold, it worked. Hertz was able to generate electromagnetic waves with a frequency of around 4 meters. Let me see if I can get this to work. Oh yeah. So we know that light over here is an electromagnetic wave. Hertz was able to generate waves around here, okay? Today we would recognize these as high-frequency radio waves. And he was able to detect the waves on the other side of his laboratory, and he was able to verify that they had all the properties that Maxwell predicted. They could be reflected, they could be refracted, et cetera, down the list. So this was an amazing confirmation of Maxwell's predictions and a testament to the sheer power of his mathematical theory. Now today we know that there's a whole electromagnetic spectrum, ranging from radio waves with wavelengths that are miles long, down to X-rays and gamma rays with wavelengths comparable to the size of an atom. And Maxwell's equations are the theoretical framework that govern the behavior of all of these different kinds of waves. They all travel at the speed of light, etc. Okay, now this was a long digression into electromagnetism, but there's a reason I wanted to explain all of this. Let me summarize the story I just told you, and hopefully you can see why it's relevant. So we have a theoretical physicist who develops a set of field equations to describe everything that's known in a particular area of physics. The equations predict that the fields they describe should be able to propagate as waves. But this is a purely mathematical prediction. Nobody's ever detected these kinds of waves before. Then, decades later, in a stunning confirmation of the theory, scientists are able to detect these waves for the first time. Now, does any of this sound familiar? So this is exactly the story that we're telling about Einstein. When Einstein began his work on gravity, he had the example of Maxwell to follow. And he had a whole conceptual framework of tools at his disposal based on electromagnetic theory. He had the concept of a field, and he had the idea that fields can propagate as waves. So essentially, in a nutshell, what Einstein did is he found the equivalent of Maxwell's equations, but for the gravitational field. And his prediction of gravitational waves is very similar to Maxwell's prediction of electromagnetic waves. It's a purely mathematical prediction based on these field equations. So let's turn now to Einstein's work on gravity. I mentioned earlier it was only after 1905, after publishing his special theory of relativity, that Einstein got serious about gravity. Special relativity deals with objects in a state of uniform motion. In other words, it only applies to objects that are either at rest or moving in a straight line at a constant speed. So they're not accelerating or changing direction. It also doesn't incorporate the effects of gravity, which would cause objects to accelerate or change direction. So this is a very kind of limited, restricted theory. What Einstein was trying to do after 1905 was to find a more general theory that would apply to things in any state of motion, even if their motion is changing. So he was trying to generalize his special theory of relativity. Now it turns out that there is a very deep connection between motion and gravity. There's a very deep sense in which gravitational attraction is just a kind of motion. This goes by the name of the equivalence principle. And I think I'm not going to get into it now. I don't think it passed the daughter test. So I can say more about it during the Q&A, but I'm not going to go into it now. Okay? The point is that in trying to generalize his theory of motion, to try to find a more general theory of motion, a general theory of relativity as opposed to the special theory of relativity, what Einstein quickly realized is that this would lead to a new theory of gravity. So that's what he set off to find, a new general theory of motion and gravitation. Now, it took him 10 years to get there. It was 1915 by the time he worked out all the mathematical details. And he published his general theory of relativity in 1960. Now, part of the cultural mythology around Einstein is that he was sort of an abstract theoretician with his head in the clouds, and he had no concern for experiment or for observational fact. In reality, nothing could be further from the truth. He was bold about drawing conclusions that seem to fly in the face of everything we know. But that's not the same as being dismissive of facts. In reality, Einstein was well acquainted with the cutting-edge discoveries in the laboratories and astronomical observatories of his day. And he was deeply concerned with grounding his theoretical work in observational fact. Now, part of his challenge is that he was trying to develop a new theory that would replace Newton's theory of gravity. So he needed to find things that his theory could explain, but Newton's theory could not. But on the other hand, his theory also had to agree with all the correct predictions of Newtonian gravity that were known to be highly accurate. Otherwise, his theory would just be wrong. Now, Newtonian gravity was an incredibly successful theory that gives extremely accurate predictions for almost everything. So it's not like there was like a whole list of things that Newtonian physics couldn't explain. Reality wasn't exactly crying out for a new theory. Okay? So this was a real challenge, right? There wasn't a ton of observational evidence that Einstein could point to in support of his theory as an extension of Newton's theory. But there was one very significant observation that proved to be decisive. By the end of the 19th century, people had developed Newton's theory to the point where they could calculate extremely accurately the exact motions of the planets in our solar system. And astronomers had developed their telescopes and their measuring ability to the point where they could measure the exact motions of the planets extremely accurately. And in almost all the cases, the observed orbits agreed with the theoretical predictions with mind-boggling accuracy. But there was one exception to this. When they calculated the orbit of the planet Mercury, they found that their prediction disagreed with the astronomers' measurements by a tiny amount. Now, the discrepancy was so tiny that it's hard to believe that either the theory or the observations could possibly be so accurate. But they actually were, and this was a real example of something that Newtonian gravity couldn't explain. Now, Einstein struggled for a long time to find his new equation for the gravitational field. And when he finally thought he had it right, that he had the correct final form of the general theory of relativity, he decided to try to use it to calculate the planetary orbits. And what he found was absolutely stunning. I get the word stunning from Yaron Brook. He uses that all the time. It's a great word, though. What Einstein found here was absolutely stunning. So his new theory agreed precisely with the Newtonian calculations for every single planet except, you guessed it, Mercury. And in the case of Mercury, Einstein's theory agreed precisely with the astronomers' measurements. So Einstein's theory got the orbit exactly right. The two theories agree on the motions of all the other planets, but in the one case where Newton's theory got the motion wrong, Einstein's theory got it exactly right. So this was decisive evidence supporting the new theory. Apparently, when he got this result, he was so excited he couldn't work for 3 days. He just sort of danced around his apartment. Now, over time, people have identified more and more ways that general relativity differs from Newtonian gravity. And they've tested it against observations, and it's passed with flying colors every time. One implication of general relativity is that light is affected by gravity. Its path can be bent by strong gravitational fields. One of Einstein's first predictions, in addition to this Mercury calculation, was that the sun's gravitational field ought to be strong enough to deflect light rays by a measurable amount. So Einstein calculated exactly how much the light should be bent. When he published his theory in 1916, he mentioned these two things, the orbit of Mercury and the bending of light. In 1919, astronomers were able to make very precise observations during a solar eclipse of the light grazing the sun. And what they found confirmed his prediction. So this is another strong piece of evidence in support of general relativity. Now, yeah, this was the New York Times. The rest of the headline was a bit nutty. Now, if light is affected by gravity, that implies another possibility. What if the gravitational field is so strong and its pull on light rays is so severe that the light can't even escape? Almost immediately after Einstein published his theory, a German astrophysicist named Karl Schwarzschild used general relativity to calculate the gravitational field around a star. And if you look at Schwarzschild's solution, what you find is that it does indeed predict a region where gravity is so strong that light can never escape. Now, on the other hand, you only get this no-escape region if the star is compressed down to a tiny volume, way smaller than any stars known at the time. For instance, for a star that has the same mass as our sun, this no-escape region would only form if all of that mass were compressed down to a radius of less than 2 miles. So now the actual radius of our sun is more than 400,000 miles, okay? But if you could somehow compress it down to less than 2 miles, you'd get an incredibly strong gravitational field, and you'd get one of these no-escape regions. Now, what would be a good name for a region where gravity is so strong that nothing that falls into it can ever get out, and even light can't get out, so it's completely black. So it's like a hole in space that's completely black. Okay? So this was the theoretical prediction of a black hole. Now, for a long time, people didn't really take this idea too seriously. You know, even Einstein was skeptical that an object like this could actually exist. But one of the things that happened in the 20th century is people studied more and more what happens to stars after they burn out. And as they started to get a better understanding of it, eventually this idea of a black hole became more and more inescapable, no pun intended. Basically, after a star is done burning up all of its nuclear fuel, it explodes in a giant supernova. and most of its mass flies out into the universe. But some of the matter remains and collapses back together, pulled in by its own gravity. Now, what happens next depends on how massive the remnant is. If the remnant is less than around 1.4 times the mass of our sun, it'll stop collapsing when it reaches roughly the size of the Earth. Okay? So you have a burned out star that's roughly the mass of the sun, but the size of the Earth. This is an incredibly dense object called a white dwarf. If the remnant is a little bigger than 1.4 times the mass of our sun, but not too much bigger, it'll stop collapsing as basically a giant ball of neutrons, like you'd find in the nucleus of an atom. This is called a neutron star. So imagine an object about twice the mass of our sun compressed down to a ball about 6 miles in radius. Okay, so this is like 1 billion times more dense than a white dwarf. And its gravitational field is so strong that these general relativity effects start to become important. Now, if the remnant is more than 2 or 3 times the mass of our sun, its gravity will be so strong that nothing can stop it from collapsing. There's no known physical process that can prevent complete gravitational implosion. So, according to everything we currently know about astrophysics, any star that starts out above a certain mass will have to form a black hole after it burns out. Today, there's all kinds of evidence drawing on all areas of physics to suggest that black holes are real and they're all over the universe. The more we learn about what's out there in the universe, the more we find that we have to make use of Einstein's theory to understand things in astrophysics. So after decades of observational and theoretical work, the result has been a steady, gradual accumulation of evidence supporting general relativity. Okay, so now I think we're finally ready to get back to gravitational waves. Einstein's prediction of gravitational waves came in 1916, and it was very similar to Maxwell's prediction of electromagnetic waves. It was a purely theoretical prediction based on showing that the gravitational field equation can take on the form of a wave equation, just like Maxwell showed with his equations. Now, Einstein himself harbored doubts about whether these waves were even real, and whether it would even be possible to measure them even if they were real. He assumed it would never be possible just because of how weak they are. But decades later, a new generation of scientists began to take this idea more and more seriously. There was sort of a resurgence of research into all these things, black holes and gravitational waves. And the gravitational wave research delved really deeply into 2 parallel questions. One was the question of what kinds of sources out there in the universe would produce gravitational waves. And 2, the question of whether it would be possible to build a detector that could measure them. So let's look at the question of the sources first. One of the most promising types of sources for this kind of thing is a pair of massive bodies in orbit around each other, a binary star system, for instance. According to Newtonian physics, a pair of stars in orbit around each other would just continue to orbit around each other in perfect elliptical orbits forever. They would just keep going on these perfect ellipses. There are no gravitational waves in Newtonian physics. But Einstein's theory predicts that a pair of stars that are orbiting around each other like this would lose energy by radiating gravitational waves out into the universe. This would cause them to gradually spiral closer together and speed up in their orbits. I think that's an artist's depiction. Now, is there any evidence to suggest that this actually happens? Well, it turns out that the answer is a resounding yes. In 1974, 2 astronomers discovered a binary star system consisting of 2 neutron stars in orbit around each other. Remember that a neutron star is basically a ball of neutrons about twice the mass of our sun, but with a radius of about 6 miles. So they have extremely strong gravitational fields. Now this particular neutron star binary was interesting because one of the neutron stars is a pulsar. A pulsar is a neutron star that emits a beam of radio waves that sweeps around as the star spins. So it's like a lighthouse. And what we observe from Earth is the extremely steady pulses of radio waves, like the ticking of a very accurate clock. Okay? Now, you can use this very accurate clock to give you very precise information about how these stars are orbiting around each other. So these two astronomers, Russell Hulse and Joe Taylor, observed this binary pulsar system over a period of many, many years. And what they found was that the orbit was indeed speeding up. Now, when they compared their measurements to the change in the orbital period, when they compared their measurements of how the orbital period is changing to the theoretical prediction from general relativity, what they found was, again, absolutely stunning. Okay, so the solid curved line in this graph is the theoretical prediction from general relativity. So the solid curve here, do it on the side too. The solid curve, so it's telling you how the orbit of these stars should change if the system is radiating energy away in the form of gravitational waves. So the orbits are speeding up, so their period is getting smaller, right? So that's why it curves down like that. The dots in this graph are the measured changes in the orbit of the binary system. And what you can see is that there's absolutely spectacular agreement between theory and observation. Over a period of 30 years, these stars have been losing energy by the exact amount that general relativity predicts they should if they're radiating gravitational waves. So this is decisive evidence that gravitational waves are indeed real. Hulse and Taylor won the Nobel Prize for this in 1993. Now, at the same time, I think it's important to note that this is indirect evidence for gravitational waves. We're not actually detecting the gravitational waves being emitted by this neutron star binary. What we see directly is how the binary pulsar's orbit changes, right? And from the change in the orbit, we infer that it's radiating gravitational waves. So the next question is, are there sources that emit gravitational waves that are strong enough that we might actually be able to detect them on Earth? Now, there's been a lot of theoretical work on this over the last 50 years. What are the most promising sources? How strong are their gravitational waves? For what it's worth, this is the kind of work that I was doing when I was a grad student and postdoc. Now, there are actually two parts to this question, of course, because whether there are waves that are detectable doesn't only depend on the waves, it also depends on the detector, right? So while the theoretical physicists were sort of extracting every ounce of possible mathematical insight from Einstein's equation, there was a whole other parallel track of work exploring how to push the boundaries of technology to make a gravitational wave detector with the greatest possible sensitivity. And the result of all of this work was the firm conviction that it was not completely crazy to think that we might actually be able to detect these things. So between the theorists and the experimentalists working in collaboration, there emerged a project that eventually became known as Ligo. So LIGO stands for Laser Interferometer Gravitational Wave Observatory. And what I'll do is I'll go through each of these one at a time. So the word laser interferometer is there in the name, because the way these detectors work is they rely on wave interference. It's an interferometer. Let me explain this a little. So now there's a lot of detail on this graph, but don't worry about too much of the details. Imagine you take a laser beam and you split it into two beams that travel down perpendicular paths. So you have a laser beam, I'll do this on both sides, and you've got a splitter here, and then one beam goes this way and one beam goes that way, okay? And then it bounces off this mirror and comes back. So it splits over here, goes down this arm, one goes down this arm, one goes down this arm, and then they come back and they recombine in a detector, okay? Now the laser beams are light waves. So when they recombine, what you're detecting, what you're recombining is the light waves from each beam after they've traveled down these different arms of the interferometer. Now waves have interesting ways of combining with each other. If the arms that the beams travel down have exactly the same length, when they recombine, the waves are going to be in sync, right? So they're each traveling down, they bounce back and they come back. If the arms have exactly the same length, the waves will be exactly in sync. And if they're in sync, they're going to add together and make a brighter image. That's called constructive interference, right? Now, if the arms of the interferometer have a slightly different length, okay, when the waves recombine, they're going to be a little bit out of sync. And instead of adding up, they'll cancel out a little bit, okay? So the way an interferometer works is you record the pattern of how the laser light waves interfere with each other after they recombine. And what that tells you, it gives you a very, very accurate measurement of the difference in the arm lengths of the interferometer. Does that make sense? Sort of? Sort of is good enough for what we're doing here. So if it sort of makes sense, that's perfect. Okay, so what you're getting is a very accurate measurement of the difference in arm lengths of this interferometer. And the beauty of this is that's exactly what you need to detect a gravitational wave. When a gravitational wave passes along, what it actually does is it changes the spatial relationships between objects. So here we have some objects. So when the gravitational wave passes along, what it does is it stretches things out in one direction while squeezing them together in another. And then it does the opposite. Back and forth, back and forth and back and forth. And again, this is because gravitation is related to motion. That was that equivalence principle that I didn't explain. So when a gravitational wave passes by the interferometer, okay, so imagine you've got these perpendicular arms, right? When a gravitational wave passes through the interferometer, each arm of the interferometer is getting longer and shorter. The arm lengths get alternately squeezed and stretched as the wave flows by. Now the cool thing about this is because the arms are perpendicular, the stretching and squeezing happens out of sync, okay? So the arms end up having different lengths as the wave passes by. And that difference in the arm lengths is exactly what the interferometer measures. So that's how you detect a gravitational wave. Now, the challenge with this is that any gravitational wave that's passing by the Earth is going to have a really tiny effect, okay? So you're measuring the difference in the length of these interferometer arms, okay? The change in the length of the interferometer arms, you can calculate this using general relativity, it's going to be around 1 part in 10 to the 21st power, okay? So that's a 1 with 21 zeros after it. As my son would say, this is like 1 in a schmagillion. And the problem is that random variations in the environment can have a much bigger effect on the lasers and mirrors than that, okay? If someone just walks down the hallway or sneezes in the control room, that's going to shake the lasers by more than 1 in a schmagillion. So the whole challenge is to figure out how do you eliminate all the possible sources of random noise and to ensure that when you get a signal in the detector, it's actually a signal that's caused by a gravitational wave passing by. Now, the engineering side of this is definitely not my area of expertise. I'm even less of an engineer than I am a philosopher. So the only thing I'll note here is that this is part of the reason they built 2 of these detectors. If someone sneezes in the control room in Hanford, Washington, that's not going to shake the mirrors in Livingston, Louisiana. Okay? So by comparing the output of the two detectors 2,000 miles apart, you can start to get at the answers. Okay, so this Ligo project was a huge decades-long effort involving hundreds of scientists and engineers. They actually broke ground and started building these things when I was a grad student in the 90s. And they first started taking data around 2002. Now they built and tested these things in stages. The first generation of detectors was not really considered to be too likely to see anything. In 2010, they took the detectors offline and started upgrading to an advanced design that was much more sensitive. And in fact, the advanced detectors are sensitive enough that it would have been surprising if they did not see something. If they turned these things on and never ever detected a gravitational wave signal, that would actually call into question a lot of the things that we know about astrophysics. So in 2015, the advanced detectors finally came online. And before they were even done testing them out, they were still doing engineering runs to make sure they were working properly. Bam! They detected the first gravitational wave signal. Now, as I mentioned at the start of the talk, the signal came from the merger of two relatively small black holes around 1.3 billion years ago. Since then, there have been at least 5 more detection events, most of them also coming from the merger of a binary black hole system. So this brings us to the O in LIGO. And the question here is, what was the point of all this? Did we go to all of this effort and all this expense just to prove that Einstein was right? Was all of this just so that we could confirm a prediction that Einstein made in 1916? Well, think about this. For almost all of human history, our knowledge of the universe came from looking at the sky using visible light. But then Maxwell discovered that visible light is just one narrow band of a broad electromagnetic spectrum. And there's a whole range of other wavelengths out there. Eventually, people started looking at the universe using other forms of electromagnetic radiation, radio waves, X-rays, gamma rays, and more. And what happened was, every time we opened up a new band of the electromagnetic spectrum, we discovered things we never even imagined before. It completely transformed our understanding of the universe. Once radio astronomy got going, we discovered totally new objects that existed out there in the universe, quasars, pulsars, and other things we never knew about. Once X-ray astronomy got going, we got our first strong evidence of black holes. Same with gamma ray astronomy and infrared astronomy, you name it. Every new band of the electromagnetic spectrum was like a new frontier. It was like opening up a whole new window on the universe and seeing it in a way we'd never seen it before. So now consider this. What Einstein discovered is not just a new band on the electromagnetic spectrum. He discovered a whole other spectrum. Okay? It's a whole different kind of radiation altogether. We're seeing waves of gravitational energy. And now that we can detect it, we're getting a completely different kind of information about the universe. When two black holes collide, there's nothing to see using light or other electromagnetic waves. But the gravitational waves come right from the center of the collision. We're now able to peer right into the heart of events that were completely invisible to us before. So this is a new window on the universe like nothing we've ever seen before. Now, the real power of this is when we can get information from all these different forms of radiation at once. So I want to tell you about one final amazing discovery. On August 17th, 2017, LIGO got a signal that was different from the black hole collisions they'd seen before. From the shape of the waveform, they could tell that this was a neutron star collision. So this was the first time ever that we've directly detected the merger of a binary neutron star system. So LIGO gets this signal, and they immediately send out an alert to astronomers all over the world. all different kinds of astronomers immediately start looking for counterpart signals across the whole electromagnetic spectrum. Gamma rays, X-rays, radio waves, visible light, infrared. More than 70 observatories around the world got in on the action. And they all saw something new in the region of the sky where the gravitational wave signal was coming from. So here you have an astrophysical event, the merger of two neutron stars, which nobody has ever definitively seen before. And you're collecting information about it in every form of electromagnetic radiation you can, and in gravitational waves. So what was the result? Well, scientists have been studying this kind of thing for a long time. And there are a lot of theories about what would happen when neutron stars collide. But so far, we've never had direct evidence to say definitively for sure what the results would be. So let me give you an example. Neutron star collisions are believed to be the cause of a type of gamma ray burst. So these are bursts of gamma rays that we observe in the gamma ray telescopes. These are some of the brightest explosions in the universe. They happen around once a day, and there's different types of gamma ray bursts. And we've been observing these gamma ray bursts for a long time and wondering what causes these things. Now, there were solid lines of evidence supporting the idea that this particular type of gamma ray burst was caused by colliding neutron stars. But up until now, there's never been any direct proof. So this was an open question for many years. So what happened with this event was about 1.7 seconds after the gravitational waves arrived, the gamma ray telescopes detected a gamma ray burst from the same event. Okay? So right away, just from that alone, we know that it's a neutron star merger from the gravitational wave signal. We see the gamma ray burst 1.7 seconds apart. Just from that alone, we have conclusive direct evidence linking this type of gamma ray burst to a neutron star collision. So boom, decades of theoretical research confirmed in 1.7 seconds. So what else? Well, again, theory predicts that when neutron stars collide, nuclear reactions will create huge quantities of heavy elements. Elements like gold, platinum, uranium, and rare earth metals. And the collision results in a huge explosion that blasts these elements out into the universe. So scientists have believed for a long time that neutron star mergers are an important source of the heavy elements that we find in the universe. Again, this was an open question. So what happened? Well, because of the gravitational wave signal, all these different astronomers knew that what they were looking at was the aftermath of a neutron star collision. And when they analyzed all the different electromagnetic signals, you can use that to get information about the matter that's ejected. Okay? When they analyzed their data, they found that this collision event produced something like 200 times the mass of the Earth in pure gold, and about 500 times the mass of the Earth in pure platinum. So, another theory confirmed. The gold in your jewelry, in all likelihood, was formed billions of years ago by two neutron stars colliding. This also allows us to measure the speed of gravitational waves. Now, according to general relativity, gravitational waves move at the speed of light. Okay? But with this event, we can actually measure it. Remember that the gamma ray burst gamma rays are a form of electromagnetic waves, so the gamma rays are going to travel at the speed of light, right? And we got this gamma ray signal. So the gamma ray signal arrived less than 2 seconds after the gravitational wave signal, after they both traveled across the universe for more than 130 million years. Okay? So this event happened 130 million years ago. The waves have been flying to us ever since, and they arrived less than 2 seconds apart. So what that means is that to within an accuracy of 1 part in 10 to the 15th power, the gravitational waves traveled here at the speed of light. So we have, the first time ever, we have an actual measurement of the speed of gravitational waves. So I could go on and on. I'm kind of geeking out here. There's so much that scientists have been able to learn just from this one detection event. And this is only one event. I mean, imagine how much more we'll be able to learn about the universe after this sort of thing becomes routine. So this is a whole new era of observational astronomy. So let me wrap up here. The title of this talk is More Things in Heaven and Earth. And this was a deliberate reference to Hamlet's statement to Horatio that there are more things in heaven and earth than are dreamt of in your philosophy. Now, I think that this quote is sometimes taken to imply a dismissive attitude towards human knowledge, and I certainly don't mean to imply that. What I wanted to emphasize by using this quote is the idea that philosophy is a very delimited science, again, as I said at the beginning, especially metaphysics. It can tell you some things with certainty, but it can't tell you everything. And one needs to be very careful to distinguish what kinds of things it can and can't tell you. The history of science is actually full of surprising discoveries that profoundly changed man's view of the world. Think about this. So we all accept the idea that the Earth orbits the sun, right? But if you do the math, this actually implies that we are hurtling through space at 70,000 miles per hour. I mean, what were Copernicus and Galileo thinking? That's crazy, right? The theory of evolution implies that all life on Earth is related on one gigantic family tree. So if you think about it, that means that we are literally the distant cousins of hummingbirds and cauliflower. I mean, that's not easy to wrap around. I mean literally, not the way they use literally today. So today we have a theory, Einstein's General Relativity, that proposes that there is a deep connection between the gravitational field and the spatio-temporal relationships among entities in the universe. It implies that in some sense, part of the role of the gravitational field is to define the spatio-temporal structure of the universe. Is that weird and hard to wrap your head around? Absolutely. Is it obviously in conflict with the objectivist metaphysics? I don't think it is. So, what I hope I've been able to do in this talk is give you some appreciation for Einstein's theory of gravity, and to show you that it's become an indispensable tool in our ongoing quest to understand the universe, and how it's now given rise to a whole new way of studying the universe that was unimaginable just a century ago. Thank you. Okay, now just one caveat here. I said I'm not a philosopher. I'm also, it's been 15 years since I've actually done any physics, so I may not be able to answer any of your questions, but we'll go for it anyway, yeah.
All right. The James Webb Telescope is going up in approximately 300 days.
The which one?
The James Webb Telescope.
Okay.
Do you have any ideas, expectations of what they will see?
I've never heard of the James Webb Telescope. So, like I said, you know, I'm working for the Ayn Rand Institute now. I'm totally out of science, but maybe you can. What kind of a telescope is it?
It's a telescope that is detecting in the infrared spectrum. So they're very excited what it will see, because the Hubble Space Telescope, it only detects the visible light.
Yeah.
All right.
I mean, like I said in the talk, every time, you know, a new form of electromagnetic radiation was observable, new things were discovered. I'm guessing, I mean, we have infrared telescopes already, but I'm guessing maybe this is the first space-based one. Is that right? Okay, so yeah, this will be a way to get infrared radiation without atmospheric issues and things like that. You know, when they put space-based telescopes up, it makes all kinds of new things possible. So this will, I mean, all I can say is this will add to our ability to see things and learn things about the universe. So, yeah.
I was wondering if you could talk a little bit about quantum entanglement and what you think the implications of that are.
So that would be a whole other talk.
I know, but if you could give a brief description, and then if you felt it had like do you think roughly it has a broad impact on a philosophical point of view,
Well,
or? If the answer is no, that's okay.
No, I wonder if we should take it offline, because I would first want to talk about quantum theory and that sort. I mean, the short answer is, I think part of what motivates the question is there's the claim that this phenomenon of quantum entanglement gives rise to the possibility of faster than light
Right.
causal interactions. Now, my understanding of this, again, this is not really my area, but my understanding is that, so if it were possible to send signals faster than the speed of light and to communicate information faster than the speed of light, that would lead to all kinds of paradoxes and contradictions and problems. But my understanding is that that's not actually possible. So you can have these quantum systems that are entangled and they're sort of causally related, but you can't use them to transmit information or send. And so we're sort of saved from those paradoxes by that fact.
Right. But I know they're working on like quantum computers.
Yeah, but that's a different
yeah,
phenomenon.
I'm sorry, one more. In regard to space-time and the math, which allows you to move both forward and backwards in time, and what do you think of the implications of that?
Well, the math doesn't allow you to move forward and backward in time. So let me say something about the concept of space-time. So it's a mathematical concept that we use to study the set of possible solutions of Einstein's equation. So Einstein's equation is the equation that codifies the theory of general relativity in the same way that Maxwell's equations capture the theory of electromagnetism. And one of the things that you do in physics is you take a physical situation and you apply the equations to that physical situation and get a solution, and then you can study the properties of whatever you're looking at. So solutions to Einstein's equation are space-time. So it's sort of the entire universe projected all the way forward and backward in time, and that's what you're solving for. So, and the whole idea of this is that it's sort of an idealized mathematical solution that you can use to study the properties of real things. So just to give you an example, I talked about this black hole solution, the Schwarzschild solution. So what Karl Schwarzschild basically found was, one of the simplest solutions to Einstein's equation, which basically consists of, a spherically symmetric mass, and that's it. That's all there is in the universe for all time, okay? Now, nobody thinks that the universe consists of a single mass and nothing else for all time. But the point is that you can use that Schwarzschild space-time to study what happens outside of stars that are sort of relatively isolated. And so that's the idea, and there's all kinds of other space-times that are other solutions to Einstein's equation that you can use to study different kinds of physical situations. So, I mean, there is, and this is a result of special relativity, not even general relativity. There is a way in which our concepts of space and time get a little bit blended, but I'd have to go into a much,
Sure.
longer discussion. But I mean, it doesn't necessarily lead to, time travel or moving backwards in time. It's ways of mathematically using this theory to understand the universe.
All right, thank you.
Yeah.
Forgive me, my wording's imprecise, but I'm only gonna use ideas that you've already kind of communicated to the audience to ask this question.
Okay.
There was a previous experiment that used an interferometer really similar to the Ligo one called the Michelson-Morley experiment.
Yeah.
And again, to use the context you've already given, that attempted to detect absolute motion, whereas Ligo attempts to detect motion caused by gravitation.
Right.
Why is it that the first experiment, the Michelson-Morley experiment to detect absolute motion, failed to detect it, whereas this one succeeded? Because in both cases, or in the first case, absolute motion wasn't detected because the detector actually shrank. In this case, it's also shrinking, and so as a result, and so I'm not sure how one succeeds and the other fails.
Well, they're looking at two completely different things. So in the 19th century, let's back up a step. So when people first started developing electromagnetic theory, okay, and when Maxwell identified that you could have these electromagnetic waves, people's understanding of waves came from understanding phenomena like ripples on a pond, or, you know, so you assume that the wave is a disturbance in some medium, okay? And so people assumed that if you have electromagnetic waves, there must be some medium, and they referred to this as the ether, right? And electromagnetic waves are just a disturbance in that medium, like the ripples on a pond. But the more they started trying to develop this idea, the more the properties of this ether got weirder and weirder and weirder, okay? And it was wrestling with these ideas that led people to the idea that maybe there is no ether. Maybe the waves aren't a disturbance of some medium. Maybe what's happening is these fields actually exist as an independently existing thing, and we're just seeing waves of the field. So it's like you had water waves, and then you realize, no, the waves are not just a disturbance in the water. There is no water, there's just the waves. Okay, so the fields are what are real, and the fields can propagate as waves, and there is no need for some underlying medium to explain them. So the Michelson-Morley experiment, what it was doing was, it was started with the assumption that the universe is filled with this luminiferous ether, this light-bearing ether, okay? And that as the Earth moves through it, so if this ether exists, it has some defined frame of reference, and the Earth is moving through that. And they were trying to detect the motion through that. So on the assumption that if one arm of the interferometer is kind of going against the current and the other one is perpendicular to it, it'll have an effect on the light that passes through. And it was a null result, so there was no difference. They didn't get an interference result. So people tried to interpret this in lots of different ways. Some people tried to interpret it that the interferometer was being affected, but I mean, Einstein's solution was very simple. This whole idea that there's this medium, this luminiferous ether, is just not true, and the basic reality is the waves. And so, you know, the Michelson-Morley experiment was part of the evidence that led to the idea that we don't have to assume that light is a disturbance in this medium. So the reason the Michelson-Morley experiment didn't get a result is that the thing it was trying to measure doesn't exist. The reason LIGO was able to detect gravitational waves is that gravitational waves are real and they actually have these effects. So that's what I would say.
Thank you.
Yeah.
Good talk, Keith.
Thank you.
Could you share your thoughts on two different things? You kind of alluded to the equivalence principle and invited us to ask about that. And if you don't want to right now, that's fine too. And then the second was, you didn't use this word, but it kind of came up implicitly, singularities, and kind of your take on that as something that comes out of general relativity potentially.
Yeah, I'll take the second one first. So I didn't really have a chance to get into this in the talk. So I talked about the idea that when a star burns out, it can have these different possible end states, a white dwarf, a neutron star. But if it's above a certain mass, the matter has to keep collapsing into a black hole. And so that raises the question of, well, what happens inside the black hole? You know, does it collapse all the way to the center? And this was one of the sort of concerns that I raised at the beginning. Doesn't general relativity imply that it has to collapse down to literally a mathematical point of infinite density, right? And what would you say about that? So the answer is yes and no. The yes side of this is that according to general relativity, you can prove mathematically that you have to have these singularities. So there are these famous singularity theorems. Stephen Hawking and a guy named Roger Penrose proved in the 60s that these mathematical singularities are an inevitable result of the theory. Okay? The no part of it is this. We know that general relativity has a particular domain of validity. We know that it applies to the very large, sort of cosmic scale of things. But we also know that there's a certain realm in which we expect that it's no longer going to be valid, and that's when it gets down into the quantum realm. So when the densities reach a certain point, when matter is compressed down to a certain length, when you get down to what's called the Planck length, okay? We don't expect general relativity to be a valid description of nature anymore. And so even though it's true that classical general relativity requires that there be a mathematical singularity, you only would actually get an actual singularity beyond the point where we believe general relativity is a valid description of nature. And so you have to sort of, one of the things that people have been trying to do for decades is find an integration between general relativity and quantum theory to get, so-called quantum gravity. And there isn't sort of a final definitive version of that. And so that you'd have to know that before you could answer the question of what happens to the matter that gets compressed down all the way. So that's what I would say about that. The equivalence principle, let me see if I can do this fairly quickly. So Isaac Newton discovered a very curious thing when he was working on developing his laws of physics. He discovered that that the quantity that goes by the name of mass, okay, the sort of quantity of matter in an object, plays two very different roles in physics. In his law of motion, some of you may know that force equals mass times acceleration, right? This is the second law of motion. Mass plays the role of something that carries what's called inertia. Okay, so it's the resistance of a body to a change in its motion, right? So what Newton found is that somehow the quantity of matter associated with an object is responsible for resisting its change in motion. If it's super heavy, in order to get it to accelerate, you got to push on it with a really hard force. If it's super light, you don't have to do that, right? You don't have to push as hard to get it to have the same change in motion. So that's the property of inertia. Now, in the law of gravity, this quantity mass also plays the role of the thing that determines how strong the gravitational force is. But the question is, there's no reason why should it be the case that this same quantity, this mass that goes by the letter m, why should the exact same quantity be responsible for these two very different things? And so what Einstein, and Newton actually did experiments to test, is it actually true that the m that appears in F equals ma, the inertial mass, is actually the same as the gravitational mass? He built these pendulum, with this crate, and he put all kinds of different materials in it to see, with different kinds of material, is it true that it obeys, that the inertial mass and the gravitational mass are the same? And people have done experiments ever since then to test the difference between the inertial mass and the gravitational mass, and I think they've pushed the agreement down to 15 decimal places or something crazy like that. So the inertial mass and the gravitational mass, for some unknown reason, are exactly the same. And what Einstein concluded from that is, well, that must mean that there's this very deep connection between motion and gravitation. There are different ways that you can understand this that are more physical. So it's the idea that free fall in a gravitational field is similar to weightlessness. So if you've heard about how the astronauts do their training for weightlessness, right? They go up in this airplane, and it goes on these parabolic arcs, and so there are periods where the plane is dropping in free fall, and they can experience the effects of weightlessness. Have you guys heard of this? They call it the vomit comet because everyone throws up when they go on this thing. So that's an example of, free fall in a gravitational field is exactly like being weightless away from a gravitational field. So there's a very deep connection between gravitation and these kinds of, and inertia And that's what the equivalence principle is. I don't know if that was super clear, but that's the best I can do right now. So.
I have two questions. The first one is, do you think there is a reconciliation between philosophy and science? Or do you think that they should be like treated as separate entities, each observed in isolation to each other? The second question is, you talked about areas of open research happening within this kind of sphere. Can you elaborate on what you know about that?
Okay, so the first question, definitely, so all the knowledge is interconnected. I mean, this is sort of a principle that objectivism espouses. So you definitely shouldn't have a situation where you might have ideas in this realm that contradict ideas over here, and you're just sort of happy to let that lie. So the idea that if you have a certain perspective on metaphysics, which gives you some basic principles about the nature of reality, if there are things that physicists are claiming that contradict that actually contradict that, that's a problem, and you've got to try to figure out what's going on there. Now, I said it was an open area of research. I didn't say it was an active area of research. So the thing is, I mean, what I'm saying is that there's a lot of interesting questions that one could study at the intersection of these areas of physics, and to integrate that with principles of metaphysics that we get from objectivism. Now, in order to do that, you'd have to be deeply familiar with philosophy, and intimately familiar with the history of philosophy and with all the deep questions that people ask in metaphysics and how objectivism answers that. And you'd also, I think, have to be deeply familiar with all of the stuff that I talked about, understanding the mathematics and understanding it, it's a huge amount of knowledge that one would have to acquire. But I think it's a fascinating area to get into, because you're trying to put these things together and to make sure, do we really understand, do these things really go together in a consistent way? And what are things that we can learn by trying to make them integrate? So I don't know of anybody who is working on that, but if you're interested, that would be awesome. So, yeah.
Thanks for the talk, Keith.
Sure.
Are gravitational waves ever negatively interfering?
I mean, they can interfere with each other, yeah.
So you could make something 0G just by having two massive bodies in the right place.
I mean, the thing is, any gravitational waves that we could we do generate gravitational waves. So if I go like this, I just made gravitational waves that are flying out through the room, but I mean, 1 in a schmegillion is like, enormous. So, I mean, the point is, we're talking about two black holes 30 times the mass of our sun colliding with each other, releasing a burst of gravitational energy that's roughly 3 times the mass of our sun, converted into pure energy through E equals mc squared, okay? And then that travels for 1.3 billion years, and by the time it gets here, it's, pushes by 1 in, 10 to the 21st power. So I don't think, at least, in the foreseeable future, I don't think we're going to be using these things to make interferometers or anything, gravity interferometers or something like that. But they do exhibit all the properties of waves. They do interfere. In fact, there were, people who were studying these things in the 60s found that if you have strong enough gravitational waves that interfere with each other and that gets big enough, it could collapse to form a black hole. So, and they can negatively interfere as well. So, yeah.
Hi, I have a question that may go a little bit to philosophy in physics. I came across a book about a decade ago that referenced Hannes Alfvén, who was a Nobel laureate in physics who rejected his own idea and promoted this new idea that instead of gravity being the primary force, that it was actually electricity, and that when electricity passes through a substance of matter called plasma, that's what creates gravity, I guess. And that's At least that's how, as a layman, I understand it. And then the book was by a guy named Wallace Thornhill, who the book was called The Electric Universe Theory. And so I guess my question is, do you have any thoughts about the electric universe theory and the idea of any kind of alternate theory that might augment the fundamental principle of gravity and how physics should treat that philosophically, I guess?
Yeah, I mean, I've never heard of that theory before, or the book that you're talking about. So, but I mean, there's a lot of the results that I'm talking about are coming from very standard, well-accepted perspectives in physics. There's a lot on the outskirts of that. There's a lot of different ideas that people have proposed. Most of the time, you know, people who are trained in physics can sort of very quickly poke holes in those kinds of ideas. And so I think you have to be very careful. There's a lot of kind of fringe science. You know, when Einstein put forward his special theory of relativity, I mean, it took a long time before people could even sort of figure out that it's not self-contradictory, and there was all sorts of paradoxes that people thought happened. So I would be very cautious about you know, trying to draw too many conclusions based on things that are like I think kind of the mainstream perspective. It's pretty well integrated, and there's a lot of supporting evidence for it. And I tend not to think there's too much beyond on the fringes there.
The premise behind the theory is that if you incorporate electricity as the primary, then it solves for a lot of the special cases where relativity maybe is not really sure what the answer is. So that's
yeah, but see, I don't know the special cases where relativity isn't sure of what the answer is. So,
okay,
I mean, Einstein himself spent the last years of his life trying to go beyond general relativity to develop a unified theory of gravity and electromagnetism, and a lot of that is not really considered to be very fruitful or worth pursuing. So, you know, even someone like Einstein can kind of.
So should it be considered? Should alternate ideas be considered at all, or
if
incorporated?
Yeah, I mean, so the thing is, I mean, the way science works is if people propose alternate ideas, if there's something to them, you know, they get picked up and developed and worked with. A lot of the times, you know, there's theories that are proposed that just have no basis to them, and rightly they're left to the fringes, and that's where they kind of persist. So
Thank you.
thank you, everyone.